Mercury and Venus. Two hostile worlds that suffered very different fates. One, very much alive and seething with treacherous forces of nature. The other, a planetary carcass, gouged by millions of high-velocity impacts. Both demonstrate the true horrors of planets gone wrong. Mercury and Venus, the inner planets. Along with Earth and Mars, Mercury and Venus make up our inner solar system. Jupiter, Saturn, Uranus, and Neptune, these planets farthest from the Sun, make up the gaseous outer worlds of the solar system. Over 4 billion years, the inner planets bound enough interstellar debris to become rock solid.
Why do we study planets? Why do we study astronomy at all? We someday need to go beyond the planet Earth if we expect to survive as a species for a very long time. And we need to know what's out there and what the nature of the universe is.
We're studying worlds where things are exotic, but the basic processes of physics and chemistry at work are really the same that we see here on Earth.
Millions of miles separate us from our rocky cousins. But a tour around Venus and Mercury reveals a common DNA.
We can go to Mercury and Venus and really look at these as places, as worlds with their own histories, and then contextualize our own planet's history.
Venus is the 6th largest planet in the solar system. At its closest, it is 26 million miles away from Earth. A year on Venus lasts 225 Earth days. And if you weighed 150 pounds on Earth, you'd weigh 136 on Venus. Venus. When the ancient Romans looked up, they were captivated by its commanding presence. They named the planet after their serene goddess of love and beauty.
It's such a beautiful presence in the sky. It seems obvious the connection there.
Venus has long been considered our sister planet because of its closeness in composition, gravity, density, and size.
Venus and Earth are almost twins in a lot of ways. They're almost the same size. Venus is slightly smaller than Earth. So if Earth was a regulation basketball, Venus is a soccer ball, slightly smaller. And Venus is the closest planet to Earth. So for a long time, it was thought of literally as a twin planet.
For ages, scientists thought this twin, like Earth, was a planet covered with deep oceans, lush rainforests, and had a climate that would give credibility to the notion that intelligent life could exist there.
Before the space age, people thought it might be very Earth-like on Venus. But the paradox is when we actually got to Venus and started exploring it, the conditions were so different.
It turned out Venus was less of an exotic sister to Earth and more of an evil twin.
So here you have two very similar planets in their sort of bulk properties, but they've evolved to such different states. And that creates an interesting problem in understanding planetary evolution, a sort of controlled experiment. I take these two similar planets and let them go for 4 billion years, and then why do they end up so different?
First, some of the basic differences. Venus has been hit hard with meteors. One so strong that some scientists think it may have reversed the planet's rotation.
Venus has a very slow rotation, and it has what we call a retrograde rotation. So it spins backwards compared to the direction of spin of all the other planets.
Because of this retrograde rotation, the sun rises in the west and sets in the east. And the Venusian days are long ones. The amount of time from one sunrise to the next is about 8 Earth months. But the orbital pattern and long days aren't what make Venus so intolerable. In part, it's the wicked climate. With a surface temperature of 900 degrees Fahrenheit, Venus is the hottest planet in the solar system. Travelers there would have their trip cut short in no time.
It would take a matter of seconds, maybe 1 second before they were gone, roasted to death.
If you're an astronaut sitting on Venus without a spacesuit, then your skin's gonna crisp up. You're gonna cook just like a turkey in an oven, except much faster even.
The unforgiving heat wave is created by a process called the greenhouse effect, the identical process that keeps Earth's climate in check and teeming with life. But a closer look at Venus tells us how this common trait can be a cycle of life and a cycle of death. Today, our own temperature is on the rise, and scientists found the possible cause behind it up on Venus.
Global warming is a result of greenhouse gases that are growing and growing and growing, and therefore we're getting hotter and hotter. When we looked at Venus, we said, aha, here it is actually happening.
In the 1990s, after the Magellan spacecraft was launched, planetary watchdogs began turning to Venus to surmise just how bad it could get here on Earth.
Space exploration has told us a lot about the Earth and the environment it's in. And in fact, the greenhouse effect that everybody's talking about with global warming was actually discovered on Venus.
What they found out about Venus shed new light on how fragile Earth's greenhouse effect really is.
And Venus didn't always used to be this hot. We think that early in its history, it was more Earth-like on the surface, and it lost its oceans due to what we call a runaway greenhouse effect. So Venus is an example that certainly that global change can happen on a planet, and it's sort of a worst-case scenario. We don't have to turn Earth into Venus before we're in trouble. We just have to move a little bit in that direction. And we are moving in that direction. But the real value of studying Venus, it allows us to test our climate models.
Through computerized general circulation models, or GCMs, scientists were able to calculate temperature increases on Earth based on the amount of greenhouse gases on Venus. So just how does Venus's greenhouse effect work and make the planet so hot? This is Biosphere 2. Located along the foothills of Arizona's Santa Catalina Mountains, it was built by a group of researchers to explore the idea of colonizing other planets. It is the largest greenhouse on Earth.
Biosphere is a perfect example of a greenhouse because it's a big building with glass panes that let the sun in, and the air is really hot in here.
The solar rays that penetrate the glass panes cause the temperature inside to rise.
The air heats up, but then the air cannot escape, cannot move vertically into the atmosphere because of the walls.
The windows trap the heat, warm the building, and provide the plants and trees with a livable climate. On Venus, greenhouse gases don't exactly trap the sun's heat, but they greatly slow the rate at which it can escape.
The greenhouse effect on any planet is a situation where the surface temperature becomes hotter because of gases in the atmosphere that trap the heat while letting in the sunlight.
These same greenhouse gases that would prove to be fatal to us on Venus are essential to life on Earth.
Without the greenhouse effect, the average temperature would be far below freezing, the oceans would be totally or almost totally frozen, and it's not even clear if life would exist on the Earth.
We talked about how hot it was, but why is it so hot? The answer has to do with the atmospheric composition. It's almost all carbon dioxide there.
Carbon dioxide, or CO2, makes up 95% of the Venusian atmosphere. And that high volume of gas traps more heat.
that's going to give you a strong greenhouse effect, and that's going to make it really hot. And that's why it's so hot on Venus. It's an extreme example of global warming.
On Venus, volcanoes are the natural spring source for CO2 and other gases. It's a process atmospheric chemist Jeff Sutton studies on Earth at Hawaii's Kilauea volcano. Deep below the surface, atomic compounds ignite during volcanic activity to form CO2. The gas is born from the pressure created by the heat of molten rock, or magma.
It rises towards the surface and reaches the summit magma storage complex. The pressure is decreased on the magma. And the effect of that is to allow gases that are trapped under the very high pressure to be released and bubble out.
The Venusian surface would likely have cracks in the lava similar to these vents, where gases escape into the airstream.
Somewhere between 8,000 and 30,000 metric tons of carbon dioxide boil out of the magma chamber each day. And it amounts to something on the order of 3.5 to 5 million tons per year.
And that's just one volcano here on Earth. Venus has more active volcanoes, and that means more heat-bouncing gases.
So all the CO2 just builds up in the atmosphere on Venus, which just makes it hotter and hotter.
The 900-degree heat isn't the only trait that makes Earth's twin seem a menace. 30 miles above the scorching ground of Venus, there's havoc occurring on the planet that makes 900 degrees Fahrenheit feel like a cold front. Electrical mayhem, where split-second jolts can reach 50,000 degrees. Each spark of light contains 100 million volts of electricity. Lightning occurs on both Earth and Venus when electrical charges store up enough energy until they release a spark. Mears Oppenheim teaches planetary physics to students at Boston University. And researchers like him get in on the action at Boston's Museum of Science. In their caged lighting exhibit, 30-foot-high domes motor up to simulate how lightning is generated on Venus. And then, it's showtime.
So look at this. We're generating so many millions of volts on these domes that voltage has to escape. And it's actually ripping molecules in the air apart.
The air in the domes, like within the Venusian clouds, stirs up the electrical distribution of tiny atomic molecules.
So the ripped molecules make that light as they reassemble themselves, and that's what a lightning bolt is.
Cosmic particles from exploding stars way out in the galaxy trigger lightning. When these hit the atmosphere, they provide that spark.
These are particles that come from way out in the universe into the atmosphere and cause a shower of charged particles. And on Venus, you'd probably have real lightning to the extreme extent, contain enormous amounts of energy, and go for miles and miles.
On average, lightning hits the Earth more than 3.1 billion times a year. The number of times lightning hits the ground on Venus? 0. The atmospheric pressure on Venus is 90 times greater than on Earth because the weight of the atmosphere created by gases is heavier. This prevents Venusian lightning from hitting hard ground. Instead, it is restrained to the clouds.
There's just too much resistance in that very thick air for a lightning bolt to get through. It's much easier for lightning to discharge from cloud to cloud.
And besides appearance, there's little else that's Earth-like about Venusian clouds. In fact, the main ingredient that creates them is toxic enough to burn through human flesh. From Earth, you might be able to see Venus twinkle in the morning and evening skies like a star.
Definitely not a wallflower. It's so bright in our sky, not just because it's the closest planet to us, but because it's the most reflective planet. Because it turns out Venus is completely covered in these bright reflective clouds.
80% of the sun's light bounces off the clouds that blanket the planet. But even in the clouds, Venus, our so-called twin planet, manages to show an evil nature.
And we know that the clouds of Venus are made out of sulfuric acid, basically like battery acid. And that sulfuric acid is made by sulfur dioxide coming out of volcanoes on the surface.
Like its greenhouse cousin, carbon dioxide, or CO2, gas pressure pushes sulfur dioxide to the surface through volcanic vents. It's the same gas chemist Jeff Sutton monitors carefully at Hawaii's Kilauea volcano.
The gases, the sulfur dioxide in particular, is a noxious, toxic gas, and we wear gas masks to protect our lungs and our airway because sulfur dioxide combines with the moisture in your nose and throat and forms sulfuric acid.
Sulfuric acid is nasty stuff. You don't want to splash battery acid on you. You know, you're careful not to do that. It's basically the same stuff. So it would not be good to suddenly stick your hand into the Venus clouds.
So if a traveler to Venus could survive the acidic clouds, the lightning bolts, the toxic air, and the heat, just how would the Venusian surface look? Volcanologist Jeff Burns with the United States Geological Survey, or USGS, circles the globe to understand what drives volcanic activity on the inner planets. When Burns imagines the surface of Venus, he considers the dark, eerie wasteland of Kilauea's lava fields on the big island of Hawaii.
It's very instructive to be able to come here and study this volcano to compare it to volcanism that has occurred on the surface of Venus. We can actually come out here to the field and study things. We can actually take samples and look at them in detail.
Geologists expect the amount of volcanoes on Venus far outnumbers the 1,500 or so on Earth.
Some estimates range from 100,000 to over 1 million volcanic features on Venus.
With that many volcanoes, lava rock makes up 70% of the Venusian surface, just like it makes up much of Kilauea's terrain. The ground becomes solid when the lava cools into hard rock.
Having a rock on Earth is our best analog for trying to understand rocks on the other planets. Basaltic rocks are the most similar to the Venusian plains.
Basalt is the most common type of lava rock found on Venus and throughout the inner solar system. The minerals freeze into glass and small crystals, a total transformation from what lava looks like when it streams out of the volcano.
When lava is actively flowing across the surface, it's incandescent and typically looks red. Now, quickly it'll form a silvery sheen over the top of it, and then over a period of a few weeks will turn black, such as the lava we see around me here.
At 5 miles high, Mont Mons is the largest volcano on Venus. And it's left some tremendous lava channels in its wake, just like Kilauea did.
Now, as you can see, the structure, we have levees here on the sides, and then internal structures as well. This is similar, perhaps, to how large channels called canali formed on the surface of Venus. However, they formed at a much larger scale.
Large enough to create seemingly endless miles of canali across the Venusian landscape. Consistent in both width and depth, the canali are much longer on Venus than on Hawaii because of environmental conditions on the planet. The dense atmosphere and hot temperature slows the magma from cooling into solid rock. And with little wind and no rain to further cool the magma, lava can cut through the surface for months after an eruption before it hardens.
On Venus, if you did see layering, you would expect to see layer after layer of volcanic rock that would all be relatively black and basaltic in composition. You would probably see little bits of color due to potentially oxidized iron, which would look red. Typically, basaltic lava flows are glassy enough that, in fact, you would actually cut your hand. They can be extremely sharp. They tend to quench and form glass.
And then there are the skies. That heavy Venusian cloud cover diffuses most of the direct sunlight.
So it would be a lot darker on the surface of Venus during the day than it would be here on Earth. Also, because the light is scattered very efficiently, you tend to lose shadows. So everything is lit fairly consistently across the surface. And then additionally, because of the composition of the atmosphere, everything would tend to have more of an orangish tinge to it.
Besides canyons, jagged mountain ranges scrape the Venusian skies. The planet's highest peak is on Maxwell Monts.
Maxwell is about 35,000 feet high, which puts it at a healthy distance above Mount Everest or any mountain on Earth. Everest is something like 28,000 feet high. So it's definitely larger than anything on Earth.
Our sister planet seems to have outdone one of our 7 natural wonders. But how would the Venusian terrain measure up against another geologic feature, our canyons? The Grand Canyon, a great chasm eroded over 250 million years by the Colorado River.
When the Colorado Plateau was uplifted millions of years ago, it gave the water more energy to cut back through the canyon and wear away the rocks.
The vast canyons on Venus may have also been formed by erosion, but not by a river.
Volcanic systems can erode canyons by having fluid flow if it's very fluid, not very viscous. Materials can erode similar to water. And the Grand Canyon is only part of the Colorado River system, but even looking at the Colorado River system as a whole is not nearly as long as the longest channels on Venus.
Had the ancient Romans known about the volcanoes, acidic clouds, lightning bolts, toxic air, and that scorching heat, perhaps they may have named our evil twin planet after something other than their goddess of beauty and love.
There's irony there because, of course, the Greeks and Romans didn't know anything about the conditions on Venus. And then here we are a couple thousand years later, and we're actually exploring this place, and, well, it's not quite so nice according to our taste.
But how do the dangers found on our sister planet compare to the cosmic violence on Mercury? "48 million miles away from Earth, Mercury's dust-covered hills and empty plains stretch as far as the naked eye can see."
It's a colorless body. I mean, it does not have really any colors like you see on Mars or the Earth or even Venus for that matter.
Dr. Robert Strong with the University of Arizona's Lunar and Planetary Lab has been a chief authority on planetary geology for more than 35 years.
Mercury is the innermost planet, and it's quite different than anything else in the solar system.
At 36 million miles, Mercury is the closest planet to the Sun. The planet has no known moons. Mercury has no atmosphere. And it's a naked eye planet, visible on Earth during the twilight hours. With a diameter 60% smaller than Earth, Mercury is the solar system's scrawniest planet. Much too small to generate the strong gravitational field needed to retain an atmosphere.
Gravity depends upon the mass of the object, on the mass. So the larger the mass, the more the gravity. So on Mercury, the gravity is less on there.
Since the planet's gravity is so weak, if you weighed 150 pounds on Earth, you'd only weigh 57 pounds on Mercury. Planet size matters when it comes to the internal heat needed to sustain geologic activity.
The internal convection currents that drive geology stop, and in general, it just freezes up and there's no way to sustain that geological activity. And that happened to Mercury a long time ago, probably after less than 1 billion years of its life.
The days when the planet beat with a strong pulse that produced volcanic and tectonic Mercury quakes are long gone.
Is Mercury a dead planet? Depends on what you mean by dead. Is it internally active now? Probably not. It's probably not active at all.
It is essentially a dead planet and has been dead for about 4 billion years.
For a near lifeless planet, Mercury still has some movement. Named by the ancient Romans after the swift-footed messenger god, Mercury orbits the Sun in 88 Earth days, the fastest of any planet. But when it comes to the time it takes Mercury to spin on its own axis, the planet holds the record for being the slowest. Length of time, around 180 Earth days, about half a year. The Sun's gravitational force creates a tidal friction within Mercury, which slows down its speed as it spins on its axis. This means a year on Mercury is shorter than a day on the planet. And that sluggish rotation gives Mercury a somewhat peculiar weather forecast. For 6 months, the side exposed to the Sun reaches 800 degrees Fahrenheit. On the other side, the temperature drops to 300 degrees below zero.
It has a long time to heat up on the side facing the Sun and a long time to cool down on the other side. And that's why it has these huge temperature extremes.
Despite its close proximity to the Sun, Mercury is a bit of a black sheep in the planetary family. Its skies always seem like starry nights.
The skies would be black. The reason we have blue skies on the Earth is because of our atmosphere. Nitrogen scatters light preferentially in the blue, and so that's why the sky looks blue. Mercury doesn't have an atmosphere, so the sky would be black.
Legend holds that Mercury, the Roman god, invented the sport of boxing. This is one planet that's taken the lion's share in the ring. Mercury has had millions of meteors and asteroids explode on its surface because it doesn't have an atmosphere to protect it. Our atmosphere guards Earth from most impacts, like a force field. When a small object slams into it, usually at more than 10 times the speed of a bullet, the collision with air molecules vaporizes it into a gas.
The Earth is shielded from small impacting objects by this wonderful thing that we call the atmosphere. And for small objects, weak objects, they will be completely destroyed by those forces long before they get here to the geologic surface of our planet.
On Mercury, without that atmosphere, the asteroids and meteors smack down at full throttle. This makes Mercury the most heavily cratered planet in the solar system.
You cannot take a step on Mercury without encountering an impact crater.
Back in 1974, the Mariner 10 space probe mapped half the planet's surface, including the largest crater ever surveyed in the solar system.
The most prominent feature is a feature called the Caloris Basin, which is a very large impact crater that is about maybe 900 miles in diameter.
900 miles in diameter. That's a couple hundred miles broader than the entire state of Texas. Researchers speculate the iron meteorite that made that impact stretched for more than 60 miles before it crashed into the surface. Moments after impact, seismic waves converged at the antipodal point, the spot on the exact opposite side of the planet.
The seismic waves, the shock waves from this thing traveled, and they've concentrated simultaneously around the other side of the planet and literally shook apart the surface.
The seismic turbulence jumbled up the crust and twisted the terrain into unusual rock formations.
There's all this weird terrain. In fact, the technical term is weird terrain. Because you look at it and it's just weird. It's this jumbled up and hilly and doesn't make any sense according to most geological activities. It's just very rough and looks as though somebody kind of scooped up the surface and just kind of dropped it down.
Pre-existing craters suddenly became crude hills, some 6 miles wide and a mile high.
In fact, the amount of surface elevation could have been on the order of 1 kilometer or 2 in just a few seconds. It would have been horrendous.
Scientists have no way of knowing exactly when the Caloris impact happened, but they can surmise one thing. If an asteroid the same size crashed into the Earth, the impact would be catastrophic and wipe out human civilization. Countless meteor and asteroid impacts have left Mercury scarred with dents and crater rings. Today, the planet looks beaten, a terrestrial corpse. Like Mercury, Earth's surface is vulnerable to bombardment. And Arizona's meteor crater is one of our most preserved and Mercurian craters. The desert basin has given geologists a better understanding of what happens when a meteor strikes Mercury's surface. Upon impact, energy from the shock wave rips through the surface and moves tons of rock upward to shape the crater.
And that flow of rock excavated this bowl-shaped cavity and deposited debris on the landscape for kilometers around. Same energy swept up the crater walls and caused these flat-laying layers of rock behind me to actually be uplifted. And the rock, under the influence of shock, wasn't behaving brittly like rock does, but more like taffy. This is one of the hallmarks of impact craters, not only here at Meteor Crater, but anywhere in the solar system.
But imagine if the mighty object that formed Mercury's Caloris Basin crashed down on the site of Meteor Crater.
It would be a massive explosion with chunks of molten material flying around the Earth ballistically, re-entering the Earth's atmosphere and causing just massive meteor showers everywhere.
For nearly 7,500 miles, the shock wave would rip up the soil and stir up tsunamis with 2,000-foot waves.
massive tsunamis propagate around the Earth and inundate much of the world's coastlines.
It would flatten Las Vegas, Nevada, the cities of Salt Lake City, Utah, San Francisco, California, and Los Angeles would vanish in a split second.
Shock waves from the impact would propagate through the solid Earth thousands of miles from the site of an impact like that.
Those seismic waves would converge at the impact's antipodal point, off the coastline of Africa's Madagascar, at the bottom of the Indian Ocean. Suddenly, a mountain range would explode through the ocean floor and crash up to form that weird Mercurian terrain.
Like an unbelievable earthquake, probably everywhere on Earth for an object that large.
Meteor crater would be a nick in the surface compared to the Mercurian gash left behind from a Calorus-type impact. The gouge would consume a quarter of the continental United States.
An object that size would eliminate a large portion of the west coast of the U.S. if it fell, say, on Arizona. It would literally change the coastline in an instant.
Back on Mercury, those craters give it an iconic stature in the solar system, and some of these pockmarks harbor mysteries. When the radar at Puerto Rico's Arecibo Observatory honed in on Mercury's poles, it picked up something that left researchers befuddled.
Ice, of all things. One of the hottest bodies in the solar system, and it has ice in the poles. And the reason it has ice there is because Mercury is a heavily cratered surface. And so craters in the polar regions, the inside of them, are constantly in shadow.
That's because Mercury is vertical relative to the plane of its orbit. So some crater floors never receive light or heat from the sun. But with no obvious water source on the planet, that begs the question, how did the ice get there? Scientists believe the mystery ice could have come from a comet. Comprised of rock, dust, gases, and ice, comets come from the outer reaches of the solar system, where the temperatures are much colder.
Could this ice just be on the bottom of permanently shaded craters? Or could it be ice that's sort of covered up by a layer of dust, which is shielding it from sunlight? We really don't know.
Besides these comet collisions, there is yet another type of crater on the planet, and they weren't formed by anything that fell from the sky. Instead, an Earth-like force of nature created these holes, and it generated deep from within the planet's core. Mercury. A closer look at its terrain by scientists reveals that some of its craters could have been formed from something other than asteroids, comets, and meteors.
We do understand that the dominant geologic process that affected Mercury, at least Mercury's surface, is impact cratering. The second most important geologic process to affect Mercury is volcanism.
Although we haven't seen any definite evidence of volcanoes on Mercury, we do expect that there have been volcanic eruptions in the past.
This remote cow pasture, a 3 hours drive north of Phoenix, might contain a telling link to Mercury's volcanic history. The cratered hills are extinct cinder cone volcanoes, and geologists suspect similar ones can be found on Mercury.
This is a cinder cone. You can see behind me there's a large crater in the center, which is typical of cinder cones.
These volcanoes do have their differences with Mercury's cinder cones.
Because Mercury has less gravity, we would expect the cinder cones that form to be much wider and much flatter.
All volcanoes erupt when the pressure from the magma, or molten rock inside, is greater than the strength of the rock containing it. Pressure increases for two reasons: too much magma and too much gas. And when pressure increases in a volcano, it usually has one place to go.
Lava comes up to the surface and erupts explosively. You have a vent area, and you have what's called a fire fountain.
If the pressure is great enough, its force can spew lava higher than 100 feet on Earth. But on Mercury, with such low gravity, the fountain could eject lava 30 stories high. While these cinder cones in Arizona may illustrate our shared volcanic heritage with Mercury, to witness an eruption there firsthand and watch the cinder cones form would be a whole other experience. First, without an atmosphere, a plume of ash and smoke and debris wouldn't billow across the landscape.
That material would go into essentially a vacuum of space because Mercury doesn't have an atmosphere, so that material would break up much more.
Also on Mercury, you wouldn't be able to hear the loud eruption.
Since Mercury has no atmosphere, there's no way of transmitting sound. So if you were on Mercury and playing a guitar or a ukulele or a piano, you would not hear anything because there is no atmosphere to transmit that sound. So it would be just complete silence.
Back in 1974, Mariner 10 surveyed only 45% of Mercury's surface on a flyby mission. 30 years later, NASA launched the Messenger spacecraft. The satellite will map the entire planet and transmit data to eager scientists with a deluge of unanswered questions.
I want to see the other side. I don't know what's over there, and that's been bugging me for 35 years. Is it like the side we saw, or is there something very unusual and different?
But even with resources being earmarked for future exploration of this rumpled dwarf in the solar system, exactly how different or similar we really are may be left up in the air. Despite the harsh conditions on Mercury and on Venus, a close look around our own backyards reveals the good, the bad, and the ugly of the inner planets.
The universe is this vast, vast thing, and here we are sitting on this little pinprick. I mean, we are not isolated.
We see things that happen on these other planets for tremendous climatic changes in the past that have happened in a very short period of time and changed that. And that can happen on the Earth.
Ultimately, it enriches our knowledge of who we are and how unique and how rare an environment like ours and even creatures like us might be in the universe.
And that evolution, that exploration, that turning the corner, that discovery of new ideas is what we're all about. There's a bright future.
$4.5 billion years ago, in the high-performance race to become a planet, this glistening blue sphere made it to the winner's circle. But the competition was filled with chaos and violent collisions.
But when the Earth was forming, rocks and boulders came screaming in much faster than the cars crashed when they ran into walls or other cars.
After tremendous perseverance, it became a special place in the solar system to sustain oceans, land, and life.
Bacteria help to create oxygen. We owe our heritage to the scum of the earth.
Despite modern disasters that now plague the planet, it still remains one of the most mystifying creations in the universe. Blast off aboard Spaceship Earth. Suppose extraterrestrials truly exist and want to tour planet Earth. They'd be in for the ultimate cosmic vacation. Earth, whose name may go back to the Greek word aras, meaning ground, is the third terrestrial planet from the Sun. But when arriving, visitors will realize that it got its nickname the Blue Planet because 3/4 of it is covered with water. And vacationers will see that Earth is the only planet in our solar system where humans or advanced life exists. If you can breathe our oxygen-rich atmosphere or breathe underwater, Earth can be explored without a protective spacecraft and spacesuit. But tourists will need to adjust their watches. It takes 365 days for Earth to orbit around the Sun. And each day is 24 hours, which is the amount of time it takes the planet to rotate around its axis once. Despite travelers' warnings about deadly storms and civil wars, Earth is a relatively safe adventure destination.
The Earth is a very special planet. Just like a Porsche is a very special car, our planet was formed in just the right place in the solar system. In fact, it's the only place we know of in our entire solar system where plants and animals can live under natural conditions.
Renowned astronomer Donald Brownlee has spent his career on a cosmic quest to solve the mysteries surrounding the origin of Earth. He says in the race to become a life-sustaining planet, Earth was in the driver's seat. But he cautions the ride was full of danger and intrigue.
The Earth had many things that happened to it to make it the way it is right now. And many of these things did involve luck.
4.5 billion years ago, one corner of the universe experienced a colossal fireworks display. A massive but short-lived star exploded as a supernova. The blast from this star may have triggered the gravitational collapse of the cloud that formed the Sun.
Shortly after the Sun formed, you had a lot of material orbiting around the Sun. And this was microscopic stuff, ice particles, dust. A lot of it wasn't unlike the lint that comes out of your dryer. And it began to kind of stick together in little clumps. And eventually, some of these pieces became more like sand, little pieces of silicate mostly, and it began to stick together, and you begin to get little rocks, little boulders.
As the boulders grew larger, so did the collisions. As two objects impacted, gravity held them together.
Porsches are known for speed. Planets are also known for speed. When the Earth was forming, particles and rocks and boulders came screaming in much faster than these cars crashed when they ran into walls or other cars.
Through multiple collisions, infant Earth was formed. But it would take many more impacts for it to become the size it is today. To better understand the formation process, Pete Schultz and his former student Seiji Sugita are attempting to recreate the early impacts on Earth by using the vertical gun range at NASA's Ames Research Center. It's a warehouse-sized room housing a massive light gas gun, which looks more like a ballistic missile. The vertical gun launches projectiles at specified targets inside a vacuum chamber.
The fact that this gun can load up in a different angle makes it really realistic in terms of comparison to what happened on the surface of Earth about 3.5 billion years ago.
So we're going to fire this tiny quarter-inch aluminum sphere into the chamber. And we use this because it has about the same density as an asteroid entering the atmosphere of the Earth. So it's going to slam in around 3 miles per second, about 10 times the speed of a bullet. It's going to be smashed to smithereens.
The vertical gun will shoot the aluminum bead into the vacuum chamber filled with atmospheric gases. There, it will impact a sandy mound resembling early Earth's surface.
We're in a vacuum chamber that will be putting back in a gas that will simulate what the early Earth must have looked like. Let's go ahead and make a bunch of craters, what the early landscape of the Earth must have looked like. Because these things are happening all the time, there had to have been a lot of craters. Okay. The plan is to come in, hit the center of the target, and watch the crater form. And you'll see the destructive power of this. Even though it's a tiny bead, it's going to do some real serious damage. Can you believe anything would survive?
High-speed cameras will document the impact. Schultz and Sugita nervously watch a monitor located outside the gun range.
This is the part that kills me. It's like this moment before the storm.
From a secure control room, an engineer flips several switches.
Okay, here we go.
Schultz and Sugita mix science with a little superstition.
Cross our fingers, cross our legs, cross our hands.
Okay.
This is what drives me nuts. Oh, gorgeous! Oh my gosh. Pow! Yeah.
Okay, let's take a look.
Stop. Okay.
The experiment worked.
Oh, look at this.
Oh, that is unbelievable. If we imagine this on the Earth,
Yeah?
these would be clouds that would be rolling at velocities that would be comparable to tornadoes.
Right, or even higher.
Even higher. I
Yeah.
mean, let's see what happens.
The video taken reveals a frightening and realistic picture of what happened on early Earth.
That's a brilliant wake. Okay, let's go. Enough.
Oh man, jeez. Oh, that is absolutely gorgeous. That did some serious damage. Just imagine that this is the asteroid that slammed into the Earth. This must have been happening just repeatedly, doing real damage to planet Earth. And it's just a small-scale example of what must have happened on the early Earth.
Yes! Yeah.
Some of the objects blasting into infant Earth were over 300 miles in diameter. The force of one such high-velocity impact created tremendous heat. Earth began roasting from the inside. Iron and nickel melted and sank to the core, generating heat like a massive furnace. The outer rock, or magma, was completely melted, producing a molten ocean. The planet was a raging inferno floating in space, literally hell on Earth.
The most severe impactors could have sterilized the planet. And you get a steam atmosphere and heat the entire surface of the Earth above sterilization temperatures.
Formation of the Earth's core, sometimes called the Great Iron Catastrophe, occurred within the first 40 million years of our planet's existence. And it had a profound effect on our future. Within the iron core, the rotating ball of molten iron generated a remarkable magnetic field.
This set up the conditions for a habitable planet. By getting all the iron down to the center of the planet, you had a solid core that eventually drove the protective magnetic field that surrounds our planet.
Without the magnetic field, Earth would be an airless waste, devoid of life. A gusty wind of material speeds from the sun past Earth at 1,000,000 miles an hour and could erode our atmosphere to nearly nothing in a few million years. But Earth's magnetic field deflects the solar wind and preserves our air. But even with the magnetic field, violence and chaos continued to plague our planet. Above the Earth's iron core, its rocky mantle was melting, forming volcanoes that rose to the surface and burped up noxious gases and lava. And the collisions kept coming. One impact would forever change the course of Earth's history and the fate of mankind. About 50 million years after the Earth began forming, it experienced a collision that would steer it in a new direction. An object the size of Mars slammed right into Earth, which was already 80% of its total size. The explosive impact melted both the planet's outer layers and fused the two together to form a larger Earth. Some molten debris that didn't blend together coalesced to shape our moon. Planetary scientist Bill Hartmann first proposed this theory after NASA's first mission to the moon.
When the Apollo astronauts brought back rocks from the moon, and we could actually see what the rocks were made out of, they found out that the rocks are like lava that you can find on Earth, which tells you that the moon material and the Earth material are very, very similar.
Earth's intimate relationship with its moon gave the growing planet a competitive edge.
The moon is what causes the seasons, because some parts of the year the North Pole is tilted toward the sun, and later on the South Pole is tilted toward the sun. The moon holds that tilt steady. The various gravity forces that are exerted tend to act in a way that holds that steady.
After the epic collision, which created our moon, our planet was over 90% of its total mass.
The planetary formation process involved almost a biological competition of many bodies bashing into each other at very high speeds.
When the collision subsided nearly 3.9 billion years ago, our solar system was left with 8 planets, or 9 if you still count Pluto. Earth secured the 3rd orbital position from the Sun, which is now 93 million miles away.
Planets don't like each other because they're gravitationally tugging against each other, so that they're equally spaced. Each planet is a certain fraction further from the Sun.
The objects that didn't become planets became refugees. Asteroids made of rock and iron found asylum in the asteroid belt between Mars and Jupiter. Comets composed of ices, dust, and rock sought shelter in the Kuiper belt just beyond the planet Neptune. Others migrated to the Oort cloud over 1 trillion miles from Earth.
These battered Porsches are a good analog to the early solar system, the comets and asteroids that have survived since the early days. And like these cars, which are kept here for their parts, we can also go to comets and asteroids for vital parts that have been stored since the formation of the solar system.
Over the course of Earth's history, many misguided asteroids have strayed off their orbital path and landed on our planet as meteorites. Over the years, scientists have analyzed these meteorites and determined their age through radioactive dating. And since meteorites were formed at the same time as our planets, they provide the age of Earth, roughly 4.5 billion years old.
Scientifically, this is fantastic. It's like looking into your family history and finding pieces of your first relative all the way back in Earth history. They're still out there.
Asteroids and comets may also shed light on the origins of water on our planet. $3.9 billion years ago, the Earth cooled, forming a thick silicate crust over its mantle and iron and nickel core. Warm liquid soon covered the planet's surface, except for a few volcanic islands dotting the globe.
One of the Earth's lucky properties is that it happened to be born in just the right place. It's in what's called the habitable zone. It's the right distance from the sun, where its ocean does not boil away, or it's too hot, or too far away, where its ocean freezes over.
But where did Earth get all this water? One view is that water came from volcanoes, which have been around since the early formation of Earth. Volcanoes spewed out massive amounts of steam into the atmosphere. When the Earth cooled, volcanic steam condensed into rain and thereby supplied the planet with water. But where did the steamy water emitted from volcanoes come from?
Volcanoes basically recycle material from melted rock in the mantle of the Earth, including water. But that's not really new water, in the sense that it was there before in the oceans and is coming out again for the second time.
NASA senior scientist Michael Muma says our planet's water came from space. Comets, which are made up of frozen gases, could have showered Earth with water during the relentless impacts of its infancy.
The delivery of water from an icy body depends very critically on how large the particle is. The smaller bodies that came in would break up high in the atmosphere. The other bodies deliver their material to the surface of the Earth, and they can actually vaporize that material that becomes the water on Earth.
Muma is trying to determine if cometary water is made up of the same ingredients as our planet's water. We know that the Earth's oceans contain a mixture of normal water, H2O, and heavy water, HDO, which includes deuterium, a form of hydrogen that is twice as heavy as normal hydrogen. But comets are difficult to study. Few pass near our planet because most orbit in the outer solar system. But in 1986, Europe's Giotto spacecraft had a close encounter with Comet Halley, also known as Halley's Comet, which was 38 million miles from Earth.
One of the ways we analyze samples is to fly mass spectrometers through cometary debris that's coming off the comet when it's active. And we can measure the gases very accurately in this way. This was done for Comet Halley.
Comet Halley's water is similar to that on Earth. However, the other comets analyzed so far have twice the amount of HDO, or heavy water, that's in our oceans.
We know now, by looking at other compounds in comets, that they're not all the same. So we don't know whether Comet Halley was, in fact, representative of all comets.
Most comets studied thus far have come from the Kuiper Belt, located in the outer solar system. So they probably didn't help form planet Earth. But the Gemini North Telescope in Hawaii recently discovered comets in an unlikely place. The asteroid belt, located between Mars and Jupiter. These warmer ice-bearing bodies may have the same water as Earth because they were all formed in the inner solar system, which is closer to the Sun. What's more, startling new evidence suggests that these unusual comets may not only have delivered water to Earth, they also may have seeded our planet with the building blocks of life. The origin of life. It remains one of the most puzzling and controversial questions about our planet Earth. One thing is certain. 3.9 billion years ago, humans would have lasted for only a brief moment. The Earth's atmosphere consisted of carbon dioxide, water vapor, a little nitrogen, but no oxygen. Yet, could primitive life have endured in such an environment?
We have no firm evidence that there was life 4.3 billion years ago, but we think now that the conditions were possible.
The oldest fossils on Earth only date back 3.7 to 3.9 billion years ago. Some believe that these remains once evolved in ancient ponds or lakes. There, atmospheric chemicals and energy formed a primordial soup of amino acids, the essential elements of life. But could the building blocks of life have come from somewhere else? Perhaps from an extraterrestrial object?
Meteorites contain organic materials, including amino acids. They were formed somehow in the early solar system. So there is this delivery of organic material from space.
But if asteroids and comets gave the building blocks of life a space shuttle ride to Earth, how did they survive the high-velocity impact? Back at NASA's Ames Research Facility, Pete Schultz and Seiji Sugita are conducting another cutting-edge experiment using the vertical gun range. They hope to one day confirm that meteorites and comets could have delivered life's essential ingredients to Earth.
And one of the things we are trying to look at, what is the survival of some of these building blocks? Can they be delivered to the Earth that would help seed a planet so that conditions for life could begin to exist?
Comets and asteroids probably brought essential ingredients for origin of life to the surface of Earth. The impact probably made the surface environment much more favorable for life.
Their experiments show that meteors delivered primitive carbon compounds to early Earth. Some of these compounds may have produced the building blocks necessary for life. But more research is needed.
Yeah.
So this is coming through the atmosphere,
right,
burning up as you go.
Yeah.
Still, many scientists agree the first life forms were single-celled organisms that lived in the oceans. And today, biologists are digging up the descendants of our earliest known ancestors in some of the most uninhabitable places on Earth.
If you have a big Cadillac today as modern life, ancient life was more like a bicycle. There are no remains of these organisms other than their chemistry. And I think it's important to keep in mind that for the first 2 billion years of this planet's living history, it was all microbial.
Professor Ken Nielsen is a bona fide microbe hunter. He scours the planet for the tiniest forms of primitive life that still exist today.
The earliest Earth was full of hydrogen, was full of hydrogen sulfide, had a lot of methane, some carbon dioxide. It was a place full of energy. The microbes exploited virtually every niche on this planet for energy.
Some have dubbed these early life forms extremophiles or thermophiles, organisms that can live in extreme environments.
Let's say there was a massive meteorite that hit the Earth and the temperature of the Earth went up 40 degrees. Well, that would be just perfect for these extremophiles. One of the things we know, for instance, is that the, quote, oldest organisms, the ones that are nearest to the last common ancestor, are all thermophilic organisms. And you could say, well, that proves that life evolved at high temperature.
Descendants of these hot-blooded organisms can be found today, and they can live at temperatures of 230 degrees Fahrenheit.
If you want some so-called thermophiles, then you go to Yellowstone and you see these bubbling lakes and cauldrons of smelly water. And for years, people assumed they were sterile, but they're full of life, okay? And all these organisms adapting to that extreme.
Modern-day extremophiles may prove that life could have survived and adapted under the extreme conditions on Earth during its turbulent infancy. But how could single-celled microbes transform into complex life? Approximately 3 billion years ago, primitive life soaked up energy from the sun. Underwater microbes formed a green pigment called chlorophyll. This enabled them to trap sunlight and produce a chemical reaction which converts carbon dioxide and water into food. This process, called photosynthesis, led the way for bacteria to multiply into one of Earth's earliest structures, cyanobacteria, formerly called blue-green algae. Cyanobacteria injected vast amounts of free oxygen into the water and air and sparked the oxygen revolution.
All of a sudden, life divided into two groups. One that ran away from the oxygen and hid in the anaerobic part of the world, and the other that started using the oxygen as a great energetic advantage, and then could evolve, I think, to be much bigger and perhaps to evolve much faster. One thing is for sure, when the cyanobacteria got this ability, they outcompeted everybody else.
Thanks to cyanobacteria, life was able to quickly diversify and become more complex. Without it, molecular oxygen wouldn't exist. Therefore, plants, animals, and humans would have never developed.
So if we didn't have the cyanobacteria, we wouldn't be around. We owe our heritage to the scum of the earth.
All of us came from the same place. We have so many things in common with bacteria. There's just no doubt about it.
The Mojave Desert near Death Valley in Southern California appears void of life. But below the surface of this dried lake bed, mankind's ancestors thrive. Planet Earth's earliest life forms may have adapted and persevered under extreme conditions. Today, in the parched and barren Mojave Desert in Southern California, geobiologist Ken Nielsen is searching for the secrets to life. He's discovered that modern microbial organisms also thrive in some inhospitable places.
What you see when you glance at this environment are a bunch of what appear to be tunnels or mounds here. And these are made from the gases produced by the microbes living in this mudflat area. If we were to take water and rehydrate this piece of dirt and put this under the microscope, it would be rife with abundant microbes swimming everywhere. And this is the life cycle in the salt flat, all of which we call extremophiles, and which eke out an existence in a mudflat like this.
Microbes reign supreme for much of Earth's history. They revolutionized the planet and paved the way for a myriad of sophisticated species. But it was land that gave life a new home. It's believed the emergence of landmass began roughly 4 billion years ago. Plate tectonics created heat and pressure that produced rock lighter than the ocean floor. It ultimately floated and accumulated, creating continents that would change in size and shape over time. The presence of vast continents would enable Earth to sustain its most distinctive component: complex life. After 2 billion years of planetary and biological evolution, the first plants and animals emerged from water onto land. But it would take hundreds of millions of years before humans evolved. And once man claimed dominance over the planet, Earth would never be the same. Planet Earth now holds the best real estate for mankind in our solar system. 7 diverse continents and countless islands are home to 6 billion people. Yet, remarkably, most of Earth's existence thus far has been without humans. The planet's history has been compared to a 24-hour clock, with the presence of man being the last 2 seconds of the day.
We're driving around the track now at a relatively modest speed, and this car handles very smoothly, a very controlled ride. This reminds me of life on Earth. Life on Earth has had its ups and downs, but compared to evolution on other planets, the Earth has had a relatively smooth ride for billions of years. That's why life has flourished here.
But with mankind now navigating its future, Spaceship Earth may return to its tumultuous beginnings.
Humans, through trial and error of evolution, are suited to live on this particular planet. Now that's true right now. We don't know if that'll be true in the future.
Earthlings created what once would seem almost unimaginable: technology. Mechanical vehicles, gadgets, and gizmos have simplified and bettered our lives. Many of these conveniences are run on or made using fossil fuels, which are harvested from the Earth's crust. But over the last 100 years, our innovations have gotten us into planetary trouble.
Humans are having a major effect on planet Earth with global warming and population explosion, so we're having a very large effect on the environment.
The natural greenhouse effect is the absorption of infrared radiation by our atmosphere, which warms our planet. Without greenhouse gases, the Earth's surface would be up to 86 degrees Fahrenheit cooler. But in the last 20 years, there's been an increase in greenhouse gases, especially carbon dioxide, produced by burning fossil fuels. The increased heating is affecting agriculture, sea level, and weather. In the past, carbon dioxide levels have spiked due to natural causes, such as volcanic outgassing. However, today's rises seem to be happening much more rapidly. To visibly witness the drastic changes, one needs to travel to the barely habitable zones on planet Earth. There, mankind's future is literally melting away. The Earth's north and south poles are known as the cryospheres, regions blanketed with snow and ice. They help regulate climate temperature and water levels around the globe. NASA senior scientist Walid Abdullati investigates the frozen parts of our world.
The feeling of being on the ice is amazing. It's pristine. In places, probably my boots have been the first to touch the ground there. It's very humbling. You know, you stand there and it's so vast and impressive.
But in the last century, scientists like Dr. Abdullati have personally witnessed Earth's ice shrinking. The reason? Ice and snow are white. They reflect sunlight and cool the planet. By contrast, the open oceans absorb sunlight, which heats the globe. However, as ice melts, it creates more open water, which sucks in more sunlight and increasingly warms the planet and melts more ice.
It's unstable, we say, because even the slightest change tends to amplify itself. And it's essentially a runaway effect.
Earth's polar ice caps are in peril. Continually melting of these precious landscapes may one day produce catastrophes across the planet. At the South Pole, the continent of Antarctica holds 70% of the world's fresh water. Ice shelves surrounding the continent hold back ice like the Hoover Dam, but they are weakening. After 12,000 years of solidity, the Larsen B ice shelf collapsed in just 5 weeks. At the North Pole, some predict that the Arctic Ocean will be ice-free during the summer in the next 40 to 60 years.
What's causing the warm temperatures, certainly there's an element of natural variability, but there is also a human contribution. We know that humans are contributing to the warmer environment, and that was subsequently contributing to diminished ice cover.
In Greenland, the Jakobshavn Glacier, one of the fastest flowing glaciers in the world, is now moving like a runaway train.
So it's now going about 5 feet an hour, which, believe me, for a glacier is very fast. The worst case scenario would be that all of these glaciers start to speed up and just deliver huge amounts of ice to the sea. That would be a 3-foot increase worldwide, and 3 feet in coastal regions is plenty to displace millions and millions of people.
Although humans may be able to stabilize man-made pollutants, it might take decades. At the same time, there are natural processes at work that might determine mankind's fate.
The planet's going through its own evolution. What we do on the planet affects us. It doesn't affect the planet. So we may muck up in the atmosphere for a few thousand years of global warming and so forth, but this is actually just a blip. It's an important blip to us, but it's not necessarily a blip in terms of planetary evolution.
Don Brownlee and colleague Peter Ward have measured our planet's vital signs, and its prognosis is bleak. Earth, as a place for animal and human life, is nearing old age. Why? Our sun is getting brighter and hotter.
The problem down the line for advanced life on Earth is that as the sun gets slightly brighter, the expectation is that carbon dioxide will be almost completely removed from the atmosphere. There will be an end to the age of plants and animals.
Humans could die out 500 million years from now due to the brightening of the sun. But in the grand scheme of things, man may have had a good run. Before reaching extinction, perhaps humans will have lived longer than any other complex species because of their ability to adapt to changing environmental conditions.
From a human standpoint, the Earth will remain a portion planet probably for another 500 million to 1 billion years, which is a truly awesome timescale from a human standpoint.
As Spaceship Earth maneuvers through uncharted waters, humankind can reflect on the planet's awesome achievements and steadfast survival in the tough neighborhood called the universe. It is the showstopper of our solar system. Basking in its own glow, it seduces all admirers. However, it is a beauty with a mean streak. It's a massive, frigid ball of gas surrounded by icy rings, hurtling at 40,000 miles an hour. It is a planet of violent weather with a polar storm bigger than the United States of America.
Saturn has some of the most powerful weather in the solar system. The lightning can be 1,000,000 times more powerful than lightning here on Earth.
But its moons are even more exciting.
The geysers on Enceladus are erupting water vapor hundreds of miles into the air because of the much lower gravity there and the fact there's no atmosphere holding them in.
Another has an atmosphere with oceans and mountains. Could life exist on one of these moons? Saturn, Lord of the Rings. If there is one planet that represents the majesty, mystery, and awe of the universe, it is Saturn. It stirs emotion, even from scientists who are stunned by its cosmic perfection.
You gotta hand it to Saturn for being the most beautiful thing out there. It's been my favorite planet since I first saw it through a telescope.
While it looks sleepy and serene, the sixth planet from the Sun is anything but. Saturn is a dynamo whose beauty is skin deep.
Saturn is an absolutely frigid place. You wouldn't want to step out on the surface. For one reason, you'd fall because there is no surface, but secondly, you'd freeze to death instantly.
Saturn is a hunk of hydrogen and helium that races around its axis, distorting its shape.
When you watch a professional toss a pizza, as it spins around, it flattens out. So it's the same kind of idea. Because it's spinning so rapidly, it's actually sort of squashed, sort of bulges in the middle. It's called an oblate spheroid.
Even though it's much more massive than our own planet, you'd actually weigh slightly less on Saturn than you do on Earth. A 150-pound human would weigh only 137 pounds on Saturn. That's because Saturn has such a low density, the only planet in the solar system less dense than water.
Saturn is so bloated, the gases take up so much space compared to the total amount of mass in Saturn that its density is less than 1. So if we could get somehow some really big ocean and put Saturn in it, it would float.
Saturn is the second largest planet in our solar system. It is a gas giant, a mass of hydrogen and helium 750 times the size of Earth. A day on the planet is 10.6 hours long, and it takes 29.5 Earth years to orbit the Sun. It has 48 named moons. Saturn has been around for 4.5 billion years. It formed by accreting carbon dust particle by particle into a rocky core several times the size of Earth. Then it was able to attract gases like hydrogen and helium, which collapsed under gravity.
As things started collapsing, this cloud began to compress. It began rotating more rapidly. But along its axis, from, let's say, top to bottom, it wasn't rotating, so it was free to collapse under the force of gravity.
It's called the conservation of angular momentum, a principle on display at your local ice rink.
If you push your arms out, if you're an ice skater, you'll go more slowly. If you pull your arms in, then you'll be more concentrated towards the axis of rotation, and you'll have to spin faster. And that's just what happens for a planet as it condenses.
A spinning Saturn came out of this collapsed disk. The feature that has made Saturn the most iconic planet in our solar system is her majestic, shimmering rings. They are incredibly big, 173,000 miles in diameter, wider than 21 Earths side by side.
So it would take you 2 days in a really fast rocket ship to get from one side of the rings to the other. They're huge.
However, these huge rings also are unbelievably thin, measuring about 65 feet. When viewed from the side, they virtually disappear.
They are no thicker than about 1, maybe 2 stories in a modern-day building. They're paper thin in comparison.
The rings may look like perfect solid disks. However, they are actually made up of billions of pieces of space debris. But what exactly are they?
They are countless icy bodies that range in size from objects as big as houses all the way down to the finest powdery snow you might ski on in Utah. And they're made of water ice.
They're particles that have been pulverized, so they've smashed into each other. They've broken up into many, many little particles.
If you were to be inside those rings, it'd be like in a beehive. They're all over the place, so bees in a swarm. It's a hostile place. You do not want to try to put a spacecraft through those rings.
And these particles spin very fast.
And they're screaming around the planet at 20 to 40,000 miles per hour.
The inner rings spin faster than the outer rings, and there's a reason for that.
Kepler's laws say that if you're going to orbit in a circle around a central body, if you're close up, you move really fast, and if you're far away, you move really slow.
If a particle the size of a grain of sand moving at hypersonic speed were to strike a spacecraft, it would be like a shotgun blast at point-blank range.
Now get outside the rings, things are much quieter. If you want to take a country drive around Saturn, go this way instead of following the rings.
Why the rings are there is one of the planet's great mysteries. The rings might have once been some of Saturn's moons that got too close and smashed into each other. The fractured pieces were held by the planet's gravity to become its rings. According to another theory, something big and fast might have crashed into one of Saturn's many moons. The broken shards were sucked in by gravity and fell into orbit, forming the rings. Although scientists disagree as to how the rings were formed, they do agree as to who first studied them. In 1610, the Florentine astronomer Galileo Galilei first noted the rings of Saturn.
He saw these little things sticking out on the side of the planet. He had no idea what they were. So like any good astronomer, Galileo kept a journal, and he wanted to write into his journal what he had seen, but he didn't have a word for it. So in his journal, right in with the words, he drew in a drawing in place of a noun, and this is what he drew. Here's Saturn, and here's these two things. Unfortunately, Galileo never really figured out what it was. We had to wait for a later astronomer to do that.
45 years later, a Dutch physicist, Christian Huygens, had an answer. He knew that there wasn't just one ring, but several giant rings. Today, there are 7 known ring regions.
There's the A ring, the B ring, and the C ring. So those are the 3 main rings. There is a ring interior to the C ring called the D ring. And once we got there with Voyager, it showed us the F ring in all its glory. And then there are some diffuse rings outside, the E and the G ring.
Each of these rings has a different personality. The A ring is almost transparent, which is why light easily passes through it. The B ring is dense, chock full of material. The C ring is even more transparent than the A, while the D ring is barely there.
There's a lot of neat things in those rings, so you can't think of them as a homogeneous body. You got to think of each particle inside those rings and what each one's doing.
These distinct qualities are what we see as colors, shapes, and shadows, the wonder that is Saturn's rings. The reason we can see them at all is due to the sun. Just as our moon glows with reflected sunlight, so do Saturn's rings. It is a phenomenon called ring shine.
Just imagine yourself on the night side of Saturn looking up and having the rings just completely covering the sky. It's much brighter than the Earth on a full moon.
They shimmer and they're brilliant and they're bright. And that's because they're mostly made up of ice particles, which reflect a lot of sunlight.
However, there is evidence that the glowing marvels of our solar system won't be around forever. Some scientists are asking, just when will they disappear? For all scientists know about Saturn's rings, they remain a huge mystery. When they appeared is a point of much debate. Scientists used to believe that the rings were formed at the same time as Saturn, 4.5 billion years ago.
But because we don't understand what holds the rings together, and our best guess as to how long the rings could stay together is only a few 100 million years, there's something wrong with this picture.
There are reasons to believe they're no older than a few 100 million years old. Those reasons lie in trying to estimate how much erosion is taking place on the rings because of the hailstorm of micrometeoroids, small, tiny bodies that, particles that come in at a tremendous speed and chip away at the rings and therefore erode them.
Neptune, Uranus, and Jupiter also have rings, but theirs are sparse and dim. Saturn's are bright and full, leading scientists to suggest that they haven't been exposed to erosion for long, and therefore are relatively new. But does this gradual erosion mean that Saturn will lose its most magnificent feature?
The idea is that over, long periods of time, the material can just get so small that it can be charged, end up acquiring a charge in Saturn's magnetosphere, and then it can just get zipped away, taken away by the magnetic field. Or it just spirals into Saturn itself. That is a scenario for the death of the rings, is that they finally get eroded away.
In order for Saturn to continuously have rings, they need to be refilled.
At the moment, Saturn has a tremendously large ring system, but the actual material in the rings does have to be replenished.
Strangely, another kind of assault might be necessary to preserve them.
They have to get renewed by an errant comet coming in and crashing, adding to the mass that's going around there. And that kind of question is still being debated.
The debate continues when theorizing as to when the rings will vanish.
Hundreds of millions of years, probably, maybe billions of years, we don't know. That's a matter of debate right now. Whether the rings are young and are going to die an early death, or they're old and they're going to remain with us for a very, very, very long time.
Of Saturn's 48 named moons, there are small moons called shepherds, for good reason. They have gravitational pulls that help keep the rings intact by hurting the particles. Saturn's experts are interested in the complicated choreography between the planet's moons and its rings. The contorted F ring is especially intriguing.
And then there's the two shepherd satellites on either side, Prometheus and Pandora. And they are having gravitational effects on this ring. It's being tugged in a variety of directions. So it looks wild and, misbehaved, if you will. And it's a dynamicist's playground. I mean, we're very, very interested in watching what happens to the F ring because it tells us how moons interact with rings.
Saturn mesmerized civilizations as early as 700 BCE, when the Assyrians took note of it sparkling in the distant sky. Hundreds of years later, the Greeks gave it a name, Kronos, after the god of harvest, possibly due to its position in the sky during harvest season. The Romans' god of agriculture was Saturnus, which is why we call it Saturn. They also named a day of the week after him, what we now call Saturday. However, had the Romans actually seen the planet close up, they might have named it for the god of weather.
Saturn is a wild, ever-changing place, but unlike on Earth, where things change on a daily and even an hourly basis, the storms on Saturn can last for days and weeks and months, and things change on a large scale very slowly over time.
The discovery of this violent activity on Saturn came as a surprise to experts. For centuries, their view of the planet had been obscured by an ammonia gas haze. New satellite data is changing everything.
And we see now that Saturn is a dynamic place. It's been revealed now as being probably more dynamic in a lot of ways than Jupiter. Just the number of storms we see, the motions that they do.
Incredibly, winds blow at speeds of 1,000 miles per hour.
We measure the winds literally by watching the different little cells of the atmosphere move in imaging. So you need sequential images to see how much things have moved. There are new mountains on the surface of Saturn. It's cloud features that we look at to see how quickly they evolve and change and move to measure the winds.
Recent exploration has shown other phenomena that aren't yet understood.
We can see features, clouds, eddies, big plumes of material like we see on Jupiter. And we see these oval storms, lots of them. In fact, there's one latitude in the southern hemisphere where lots of storms zip around this band, okay? And we've watched them be created. We've seen them die. They die by merging.
Scientists nicknamed this area Storm Alley, after a region in America's Midwest that produces violent weather. It is believed there's lightning there, though no one has seen it.
And there's a technical reason for that. To see the lightning, you have to get around on the night side, and because the lightning flashes aren't all that bright, and so you need the darkness. But the night side of Saturn is very bright because of all the ring light that shines down on the night side of Saturn, and so it's very hard to sort the lightning from just puffy little clouds.
The hellish weather on Saturn has one more astounding surprise. And it's a true monster.
One of the freakiest storms on Saturn was this hurricane-like thing that they found down at the South Pole. Now, this storm is bigger than the United States.
The Great Red Spot on Jupiter is merely hurricane-like. That storm doesn't have an eye wall. However, the South Pole storm has the characteristics of a terrestrial hurricane, including an eye wall, making it the only such storm on another planet.
It's not clear that it is a hurricane in every sense, like we have here on Earth, but so far the morphology of it looks very much like a hurricane. That was very exciting. Everyone got very excited about that. It even surprised us.
And you can see right down into the eye, just as you can with a hurricane on Earth, and they can see farther into Saturn's atmosphere than they've ever been able to see before. So this thing is literally a window into Saturn. And it's amazing to see something so similar to Earth on Saturn and then find out that we can actually do some science because of it.
The South Pole storm measures 5,000 miles across. That's 2/3 the diameter of the Earth. If a hurricane that huge were to form here, it would cover a distance from New York City to Baghdad, annihilating all in its path.
It's basically a swirling vortex of air that is centered around a hole right at the center with a walleye around it.
What powers this monster storm is still unknown.
And the winds are stronger on Saturn than they are on Earth, which is a puzzle in itself because Saturn gets so little energy from either the sun or from its own inside.
It's centered around the south pole of Saturn, rather than being, in the equatorial region like a hurricane on Earth would be.
In early 2007, modern imaging technology revealed something else on Saturn that astounded scientists.
We see it very, very intensely now.
It's something big, something strange, and something never seen in the universe before. Saturn, the solar system's most bizarre yet beautiful planet, has just gotten even more mysterious. In 1979, the Voyager spacecraft showed a perfect geometric form over the North Pole. In October 2006, the Cassini craft found that it is still there.
It's just bizarre, and it sits there kind of still. It doesn't move with the planet. The pole, there's a hexagonal feature, a six-sided polygon that encircles the pole at about 78 degrees north latitude. And it's sitting there as a set feature.
The hexagon is similar to Earth's polar vortex, which has winds blowing in a circular fashion around the pole. Saturn's vortex can fit 4 Earths inside of it and extends 60 miles deep into Saturn's clouds.
And what's more bizarre, Voyager saw little tiny clouds going around at about 100 meters per second, which is about 200 miles an hour, going around this racetrack. People thought, well, maybe it's just a temporary thing. How could this stay there? It's been there now for at least 20 years, and we're going, what is this?
If you go there, you're going to enter these thick clouds. And the deeper you go, the more intense the pressure is going to get, to a point when you just implode. You and your spacecraft can't make it any farther.
For now, visits to Saturn's orbit are reserved for unmanned spacecraft. But surrounding the planet are at least 48 moons. Venturing to one of those is more feasible.
What's interesting now that we're going to the planets is that we're learning that in some ways the moons are where the action is.
We've already been to one of them. Titan is the only moon other than our own to have been explored. The event was beyond significant. On January 14, 2005, science fiction became fact. As part of the ongoing Cassini mission to Saturn, the unmanned Huygens probe descended onto the surface of Saturn's biggest moon. Titan lives up to its name. It is the size of the planet Mercury. In fact, it is the second largest moon in the solar system, 50% bigger than our moon. It is seductive in many ways. For one, Titan looks much like Earth.
That was the thing that hit me over the head, just how remarkably similar in process the surface of Titan looked. We have river channels that feed into these lake beds. We have winds. And then in other areas, we have dunes. The equator region of Titan, at least on one side where we've gotten good radar imagery has hundreds and hundreds of miles of these dunes that are 100 meters high, several miles apart, and they just go on, this vast sea of dunes.
There are possibly deposits of solid hydrocarbons.
And we didn't really know until that probe landed whether it was going to hit liquid or some solid surface. It seemed to kind of fall on what looks like kind of pudding. It doesn't seem to be liquid or solid. It seems that Titan has some goo on the surface. It's almost kind of neither land nor sea, but something in between. That's very amazing.
Amazingly, Titan, like Earth, has an extended atmosphere. No other moon does in our solar system.
The atmosphere of Titan is very, very thick, very, very massive. It has a mass that's 10 times the mass of the Earth's atmosphere. And so you have a very, very thick layer of gases. So it's thicker than the air as we know it. The particles in the air are also very small, and so I would characterize them more as a haze than as a fog or clouds.
The haze is 200 miles thick, resembling something else on Earth.
From the outside, it appears essentially opaque, like a big orange ball. But as the Huygens probe descended through the atmosphere, it's transparent enough to be able to see the surface features as it fell through. But it's not unlike a hazy day here in Los Angeles.
It's not the color of the atmosphere that most intrigues scientists. It's the composition. Nitrogen and methane, the same gases they believe made up much of Earth's early atmosphere.
The idea that Titan's atmosphere mimics the atmosphere of early Earth 4 billion years ago is something we're very, very excited about and interested in, and it's one of the things we're studying very hard in our laboratory.
Let's see if we can get this aligned. What do we have?
At the University of Colorado, Dr. Margaret Tolbert is simulating Titan's atmosphere in her lab. Might it, too, have the necessary ingredients for life?
In this experiment, we're trying to simulate the chemistry that goes on high in Titan's atmosphere where the haze is forming. And so what we have is a reaction chamber here, and all that we have in there is nitrogen and methane. So the two most important components of Titan's atmosphere. And then we're just going to flick on a lamp, and that lamp is going to simulate the sunlight hitting Titan's atmosphere.
Incredibly, Tolbert's research has shown that Titan's atmosphere, when stimulated by sunlight, begins to produce organic compounds. To scientists looking for life beyond our planet, this could be big. As scientists scour the galaxy for signs of life, there are some exciting results from within our own solar system. Saturn's moon, Titan, seems to have the necessary ingredients. Testing at the University of Colorado has shown that when sunlight interacts with Titan's nitrogen and methane-rich atmosphere, organic compounds are created.
So these organics are floating down to the surface of Titan, and you can see them in the pictures, and who knows what they're doing once they're there. They could be providing energy to some new kind of life.
Further research is needed to determine if there really is life on Titan, or if it might someday develop. Although its atmosphere resembles early Earth, the environment is vastly different.
It's cold. It's 300 degrees below 0 Fahrenheit and there's no liquid water. So that's a big difference between early Earth and Titan.
The lakes and riverbeds on Titan were carved out of the ground by something. There's no liquid water on the moon, so what flows on this terrain?
The hills on Earth are made of silicate rocks, whereas the hills on Titan are ice and methane ice. The river channels on Titan are formed by methane rain, as opposed to the Earth river valleys formed by water.
Liquid methane, it seems, rains down on Titan, or did at one time.
On Titan, it is so cold that gas has liquefied, and there are coastlines and rivers and all this terrain shaped by moving rivers of methane. It's just completely intriguing.
Methane is the principal component of natural gas, butane, and propane, all sources of fuel.
There's a lot of hydrocarbons. It might be very light hydrocarbons on Titan. And there's a lot of it. And it burns if you put it in contact with oxygen. So there's a lot of energy out there.
Enough on the surface of this huge moon to supply all of Earth's needs for a very long time.
Well, here's this tremendous supply of natural gas on Titan. Boy, wouldn't it be great to go out there and tap into it and bring it back? But I think that you would find that it would cost you so much to go out and get the methane and bring it back that you would never be able to effectively power anything on Earth with it.
While Titan is Saturn's largest moon, one of its smallest may be even more exciting. It's a brilliant ball of ice and rock called Enceladus.
It's a tiny object. It's only about 300 miles in size, so that's what, about the eighth the size of our own moon. And we've never seen a body that small that has activity on it.
This activity was discovered in 2005 by Dr. Carolyn Porco and her Cassini imaging team. One photo seemed to suggest that jets were coming out of Enceladus.
It seemed very likely to the members of my team that it's possible that these jets are actually geysers. They're erupting from pockets of liquid water not too far beneath the surface.
The closest thing we have on Earth to Enceladus is something like Old Faithful Geyser here at Yellowstone National Park, which is shooting water vapor and water about 150 feet into the air. The geysers on Enceladus are erupting water vapor hundreds of miles into the air because there's much lower gravity there and the fact there's no atmosphere holding them in.
Many geysers have since been discovered, all in a region of Enceladus's southern hemisphere.
They are coming out of these fissures, these big cracks that go on for about 135 kilometers, something like 80 miles of cracks.
We call them tiger stripes because when we first saw them, they really looked like the stripes on a tiger. There are 4 areas that seem to be ridges or kind of active geologic areas, and the plumes seem to be coming out of these areas. And we've counted about 20 or 21 plumes.
Southern Enceladus is covered in cosmic Old Faithfuls.
Who would have thought that an ice ball about the size of Texas would be alive with plumes and geysers? I mean, it's astounding.
Enceladus is heated in its interior by the tides of Saturn. The Earth's moon is pulling on the Earth's oceans and distorting their shape and producing the tides that we're familiar with here on Earth. But on Enceladus, the planet Saturn is pulling on that moon, and as Enceladus goes around in its orbit, that pull is changing and the ice inside Enceladus is creaking and groaning and rubbing against itself and creating a lot of heat through friction. We think it's that frictional heat that is producing the evaporation of the water ice that is then escaping through these cracks and making the geysers that we see there.
And there's more. Enceladus's eruptions have clarified a theory of what powers one of Saturn's rings.
We knew there might be jets, something coming from the surface that was injecting material into orbit around Saturn to form the E-ring.
The E-ring is furthest from the planet, about 74,000 miles away.
It happens to be just at the same orbit, the same distance from Saturn as Enceladus. And so it really suggests that it owes its origin to Enceladus. And thickness of the E-ring sort of matches the thickness of particles that were ejected from the south pole of Enceladus.
If these geysers disappear, so might the ring. Ultimately, the liquid jets suggest that there is water on Enceladus. And perhaps something else.
So the search for water is not that, oh, one day we'll be thirsty, so we'll have something to drink. The search for water is guided by our interest in the search for life. It's that simple. Follow the water.
Saturn's moon Enceladus is one of the most exciting and least understood places in our solar system.
Enceladus is a really strange place. The strangest thing that got people's attention first is it's very, very bright. It's the whitest object in the solar system. And we now realize that it is covered in freshly fallen snow, which is the ice that's fallen back from these geysers onto the surface.
And it's that ice that has scientists excited.
Possibilities there are amazing. The search for water in our solar system is ultimately a search for life. You look for water in the hopes that maybe there will be life.
Because of the presence of ice, some experts believe the search for alien life should begin on Enceladus.
It has a lot of other molecules in it, a lot of other exotic things, which show us that there's probably aqueous chemistry going on underground. So there's a lot of little percolating kind of chemistry going on, and maybe you could get biology, maybe, and so maybe we should go look.
This is kind of the holy grail of modern-day planetary exploration, to go and seek out those environments in the solar system where life might possibly have gotten started, and we just stumbled upon it. Is that exciting? You know, I mean, of course it's exciting. It's the kind of thing scientists live for.
We know the composition of the gases that are coming out because we've flown through them with the spacecraft, and we've got the composition including carbon and nitrogen and all those goodies that you need to make life. And then we know there's a source of energy from the frictional heat or the tidal heat in the interior, and we can see the heat on the surface. So all these elements are there that might be sufficient to sustain life if life could have got started there. So that makes Enceladus a very exciting place.
But what kind of life?
We're not talking sushi, you know? We're not talking lobsters and fish, we're talking microbes. I think that's about the best that we can hope for on a moon like Enceladus. If we ever discover such life in our solar system, it's going to be the simplest possible. It's going to be bacterial, or something like it.
Even the discovery of something small would be a huge event.
It would change everything that we think and know about our solar system, the universe, and ourselves.
Much of what is known about Saturn and its moons has come from the Cassini satellite that was inserted into the planet's orbit in 2004. It is currently touring its rings, moons, and the planet itself. By 2008, Cassini will have made 70 trips around the gas giant.
Putting an orbiter around a planet and being able to hang out there and monitor the system and all the different elements of the system for a long period of time, I mean, that's the best way to study these bodies.
Scientists on a daily basis process the information sent back from these close encounters.
In addition to the camera, there's a radar that can send its radio waves through the clouds, get an echo off the surface, and make an image of the surface. And then there's spectrometers to measure the composition and other infrared devices to measure temperature. So it's a very comprehensive spacecraft.
As you see better, you learn more. I think it may have been Yogi Berra who said you can see a lot just by looking.
Relating this information to processes on Earth could help explain mysteries of our own planet.
Saturn is really very different from the Earth. Its diameter is 8 or 9 times greater than that of the Earth. Its atmosphere is made of hydrogen, completely different from our own atmosphere. But the same physics is going on. The same forces are controlling the weather on Saturn as are controlling the weather on Earth.
It is part of our history. It's the solar system. So understanding how our solar system formed is really understanding how I got here. And understanding the nature of the other planets that are in the solar system. I mean, they're like my neighbors.
Cassini's new imaging technologies are giving us never-before-seen views and information by the day. Cassini's close encounters with Saturn will bring us nearer to unlocking its secrets.
It's quite complex, and it'll take us a long time to figure it all out. I don't think we ever will figure all of it out. But it's just the beauty of being able to be in orbit and monitor a rich planetary system like Saturn's.
The Earth has a context in the rest of the universe. And you want to know where we fit in the universe? You don't get the answer to that just studying the Earth itself.
For as much as we discover about the Lord of the Rings, it will always inspire us. It's so close. For thousands of years, man has found comfort in its presence. It's been a beacon for nocturnal travelers, a timekeeper for farmers, and a location finder for sailors at sea. For some cultures, it's even been a god. It's the only cosmic body ever visited by human beings, and today, NASA is planning a permanent outpost there. But how did it get there in the first place? How did the moon come to be? The answer is more astounding and spectacular than most residents of Earth have ever imagined. At last count, over 150 moons populate our solar system. Neptune claims 13 of them. Saturn has 48. And Jupiter hosts an astounding 62. Earth, on the other hand, has just one. But it's a special one. Our moon, Luna, as the Romans named it, is remarkable in its size. It is by no means the largest moon in the solar system. Several others are bigger. One of Saturn's moons, Titan, for instance, is twice the size. But our moon is the largest in relation to its host planet.
It's a quarter the size of the Earth. It's really big compared to the Earth. If you look through a telescope at the Earth from a distance, you'd see the Earth and this other big thing. If you look at Jupiter or any other planet, you got the big planet and then little tiny moons right next to it. So our moon is so much bigger, and it's the only one of the now 8 planets that has that situation.
The relative sizes of the two bodies are close enough that some astronomers go so far as to refer to the Earth-Moon system as a double planet. The mean distance from the Earth to the Moon is 234,000 miles, a 3-day flight through space. Luna's diameter is roughly 1/4 the size of Earth's, measuring 2,160 miles. A single day on the Moon is the equivalent of 27.3 Earth days. This is because one side of the Moon permanently faces us. Luna is phase-locked with our planet. So the Moon must fully orbit the Earth in order to make one complete rotation on its axis. Sort of like children in a game of Ring Around the Rosie. They always face inward as they hold hands and move in a circle. Yet as closely related as the Moon is to our Earth, it would only take a brief visit to Luna to make it quite clear that it is in fact a very different world from our planet. And an exceedingly dangerous place.
Tranquility Base here. The Eagle has landed.
There's no air, of course, so you need your spacesuit.
Indeed, the Moon has absolutely no atmosphere at all. So there is nothing to carry sound waves. If you were standing on the Moon with a friend and tried to converse, the person wouldn't be able to hear you, except by radio.
I was strolling on the Moon one day in the merry month of December.
No atmosphere also means that there are no air molecules to scatter light from the sun. So the sky is always black. And the landscape does little to help brighten the scene.
Kind of monochromatic, you know, not much color there. The rocks are mostly gray-brown colors. It's maybe a little warmer tone in one direction, maybe toward the sun, and cooler tones, grayer tones looking in other directions, but not so colorful.
Extreme temperatures would also add to the unpleasantness of a visit. The swings between hot and cold are brutal, from 270 degrees above zero at midday to 240 degrees below zero at night. Even the Moon's low gravity, just 1/6 of Earth's, could present a hazard to a tourist. A reality the Apollo astronauts kept at the tops of their minds during their many moonwalks.
But they realized that beyond the thickness of their visor in their spacesuit was death. Should they do something and fall into a rock and lose their footing and fall and hit an outcrop, this visor could be cracked, exposed to the lunar vacuum. We would have had a serious situation on our hands.
But while a spacesuit could protect lunar tourists against the vacuum of space, a lack of oxygen, temperature extremes, and lethal solar radiation, a potential hazard a spacesuit would do little to protect against is high-velocity micrometeorites. They pummel the lunar surface frequently.
Tiny meteorites, the little ones that burn up in our atmosphere and make shooting stars, there's no atmosphere on the moon. They're coming right down, hitting the surface.
They pulverize the lunar surface, generating a dusty blanket of gravel-like material called regolith. Dr. Amanda Hendricks studies the moon at NASA's Jet Propulsion Laboratory.
This plant here is kind of a regolith factory. It's ground up rock, is what it is. The timescales at this gravel mill are a lot faster. Here, it's made in less than an hour. But on the moon, it is the result of more than 4 billion years of bombardment by meteoroids and micrometeoroids raining in on the surface and breaking up the rock.
Like the product of this gravel mill, lunar regolith has formed in a variety of grain sizes, from large rocks to fine dust.
This very fine dust is familiar to us from Apollo images that were seen of astronauts' footprints in the dust. It's very fine, and so fine, in fact, that the astronauts had problems with it sticking to their spacesuits, getting into the equipment, and it can end up causing a bit of a problem.
Really big meteorites have also hit the moon in the past. In fact, these massive impacts are responsible for the dark circular regions on the lunar surface, the shapes that to many observers seem to be arranged like the eyes, nose, and mouth of a human face. They make up the illusion of the man on the moon. They blasted huge basins in the moon's surface. Some of them are 700 miles across. Dark lava eventually burst through at the impact points and flooded the basins. Today, we call these dark regions Maria, the Latin word for seas. This dates back to the 17th century when Renaissance-era observers looked up at the moon. They speculated that the dark areas might be oceans, and astronomers of the time gave the many dark spots, or seas, whimsical names.
The seas are all named after effects that were once attributed to the moon. So you have the Sea of Storms, and the Sea of Crises, and the Sea of Tranquility, and so forth.
Some of the younger impact basins have had less time to erode, so their features are still relatively crisp. One in particular is called Mare Orientale, or the Eastern Sea. It's some 600 miles across, and the impact that created it was so massive and direct, the result looks very much like the bullseye on a target.
This Orientale scar is kind of like a bullet shot into glass, where you see all the sort of rings around it and fractures going out. People have often said if that had been on the side facing directly toward the Earth, we might have had a whole different mythology about the moon, because it would have looked like a big eye staring at us.
Three concentric rings of mountain ranges surround Mare Orientale, and some of the peaks rise to several thousand feet. They're all effects of the monster impact.
When we see mountain ranges on the Earth, they're mostly caused first by the continents moving around, crashing into each other very slowly, buckling up, and creating mountain ranges, which then erode into all the spectacular shapes that we see, the Matterhorn and so forth, from water erosion.
On the Moon, there are no continental plate tectonics. The surface is static.
Yet you still have mountains on the Moon. And the reason is that those big impact basins, that's a big explosion, excavates a pit, throws material up on the outside. So you have these rings of mountains, arcs of mountains that surround the impact sites. But they're impact features. Again, they're caused by the external forces, not the internal forces.
Another notable impact crater, much smaller than Mare Orientale, but every bit as spectacular, is Tycho. Named after a prominent 17th century Danish astronomer, this impact feature is located in the southwestern quadrant of the Moon's near side.
It's in the bright area. You can almost see it with your naked eye. And when that explosion happened, as with many other craters, it shot out jets of bright powdery dust. So there are these rays that go out from it. It's very striking.
The rays of dusty, ejected material extend some 900 miles from the Tycho impact site. A mountain of debris also rises from the center of the crater. This is a result of recoil from the asteroid strike. Some of the highly compressed material at the center of the impact site springs outward once the impacting body either ricochets or disintegrates. But long before any of the Moon's specific features could be discerned through sophisticated telescopes and space travel, careful observation of lunar behavior and appearance was still vitally important to Earth dwellers. For 15,000 years at least, man revered the Moon as a source of light, as a navigational guide, as a reference in agricultural pursuits, and most of all, as a convenient timekeeper. In the days before our modern systems, timekeeping was no simple task. Early timekeepers had two choices. They could monitor the sun or the moon.
If you think about trying to keep track of dates, if you use a solar calendar like we do nowadays, there are 365 days in a year, and that's an awful lot of days to keep track of. And it's not something that the ordinary person can do very well. Compare that with a lunar calendar. Everybody can tell when the full moon is, when the new moon is. You don't see the moon at new moon. You see it, it's big and round at full moon, so it's easy to tell. There are only 28 to 29 days in a lunar cycle, so it's easy to count them. And so most societies actually start out with a lunar calendar.
Early observers of the Moon also recognized that our planetary neighbor has a very real physical effect on the Earth itself. The Moon is responsible for the rise and fall of our ocean tides.
If we think of the Moon as being this tennis ball and the Earth as being this football, okay, the tides are caused by the Moon's gravitational attraction. So it's obvious, okay, so the Moon kind of pulls the Earth's water towards it. And so this creates a slight bulge in the direction of the Moon. What's less obvious is there's also a bulge in the direction away from the Moon. So there's, in fact, 2 high tides every day. The other high tide you can think of as being caused by the Earth's centripetal force. The Earth and the Moon are both rotating around, and that causes the water on the far side to also move out.
An extreme illustration of the difference between high and low tides can be found along the shore of Canada's Bay of Fundy. The water level from high tide to low tide drops an astounding 55 feet. For some forms of life on Earth, the advance and retreat of the tides creates useful habitats. But another of the moon's gravitational effects on our planet is directly responsible for nothing less than the continued survival of terrestrial life itself. The moon stabilizes Earth's climate. The gravitational effect of the moon keeps the degree of tilt in the Earth's rotational axis constant. This tilt is what maintains the repeatable cycle of seasons as the Earth orbits the sun.
If we didn't have the moon, or if we had a much smaller moon, for example, then you can mathematically show that the tilt of our North Pole would vary widely, with that angle going from, say, 0 to 90 degrees. Currently, it's 23.5 degrees. And it would actually vary chaotically. And so the moon has played an important role in the stability of our axis of rotation of our planet, and therefore in our climate.
Over the millennia, with the moon's prominent and constant presence in our night sky, men ultimately began to speculate on its origin. How did it form? How did the moon come to be? In 455 BCE, the Greek scholar Anaxagoras theorized that the moon was simply a rock that was flung off by the Earth. Most of his contemporaries, on the other hand, were convinced that the moon was a god, or maybe a huge ball of fire. So Anaxagoras' notion did not get much traction. Quiet speculation no doubt continued, but no hard information about the moon came until 1609, when Italian astronomer Galileo Galilei pointed one of the first telescopes at the moon and recognized that he was looking at a landscape, the terrain of another world.
When you look at the moon through a telescope, it looks completely different from the way it looks to the naked eye. Instead of looking flat the way it does to the naked eye, it really looks round, and you can see the shadows, you can see all these craters that the naked eye does not see, and it just immediately looks like a world. It jumps out at you into 3 dimensions.
Galileo made detailed drawings of the small planet's surface and established once and for all that the moon is a solid world, not a god or a fireball. But the groundbreaking astronomer never publicly speculated on the moon's origin, primarily because his interests soon moved to other planets. Not until 1873 did the first science-based theory regarding the origin of the moon publicly emerge. It sprang from the mind of a talented French astronomer named Edward Roche.
Roche advocated what's called the co-accretion theory, which says that basically Earth and the moon grew up at the same time out of the same materials.
In Roche's day, many scientists began to believe that the planets might have formed from hot condensing clouds of gas.
It gradually contracted and cooled, and as it contracted, it would separate out rings of gas. So you'd have a ring of gas here, a ring here, and so forth. And these rings of gas would then eventually coalesce and form the planets. Roche saw the Earth and the Moon as a solar system in miniature. His idea was that the Earth starts out as a ball of gas and then cools and contracts and sheds a ring of gas that then itself coalesces and forms the moon.
But there are problems with this theory. For one, our moon has a much lower iron content than the Earth. If the two bodies formed from the same materials, their basic composition should be the same, but they are not. This and other inconsistencies soon led fellow astronomers to quest for new ideas to explain the existence of the moon. In the last third of the 19th century, advanced theories about the origin of the moon started to emerge. In 1873, French scientist Edward Roche proposed that the moon simply formed alongside the Earth out of essentially the same nebular cloud of particles and gases. But this idea had a fundamental weakness. The moon has a much lower iron content than the Earth. It's much less dense.
The big thing to remember about the moon and its composition is that it doesn't have any iron core like the Earth does. So you look at the Earth, and there's a very large central area, something like half the inside of the Earth is iron, nickel iron. And that's metal that drained down to the center of the Earth when the Earth was hot, when it formed at the beginning. The moon is more like just plain rock.
Scientists initially deduced the mass of the moon through observation and mathematical calculations. If the moon had formed from the same stuff that made the Earth, the iron content should be similar. It was a hole in the theory Edward Roche couldn't explain. But another idea soon followed on the heels of the co-accretion hypothesis. In 1878, George Darwin announced his fission theory of lunar origin. This idea received some attention in part because Darwin had a celebrated father. Charles Darwin, author of Origin of Species. In time, though, George Darwin stepped out of his father's shadow and became known as England's leading expert on tides. And through extensive analysis of the tide-moon relationship, George Darwin came to the realization that the moon is gradually moving farther and farther away from the Earth.
It wasn't proved until 95 years later when astronauts landed on the moon. They put little mirrors on the moon. And you can shine a laser at the moon, and the laser will bounce off the mirror, come back, and you can actually measure the exact distance between the Earth and the moon. And the rate at which the distance is increasing is 3.8 centimeters per year.
3.8 centimeters is about 1.5 inches.
If you made a movie, extreme time-lapse, you would see the moon moving away from Earth gradually. That's what we see nowadays.
Darwin began to consider what would happen if you reversed the process, if you ran the movie backwards. As we move backwards in time and the moon moves closer, both the moon's orbit and the rotation of the Earth get faster and faster.
And so, well, what happens is that eventually the moon must coalesce with the Earth. It must hit the Earth.
The logical conclusion for Darwin was that a portion of the molten, rapidly spinning Earth must have separated from the main mass and spun off to become our moon. He immediately began work on mathematical calculations to reverse the trajectory of the moon all the way back to the Earth.
Frustratingly, he reaches a point where it gets almost to Earth, and then he couldn't work it out any farther. The mathematics doesn't let you go any farther. What you get to is a point where the moon is whipping around the Earth at a rate of 5 revolutions a day, or 6 revolutions a day. So it's just zooming around the Earth, okay? And it's about 5,000 miles away from the Earth.
Still, the mathematics did not allow Darwin to bring the two cosmic bodies into contact. The fission theory was debated for decades, but scientists eventually concluded that the relative movements of the Earth and Moon could not have resulted from it. The Earth would have been spinning too fast to account for its present rotation rate. The quest for an explanation of lunar creation continued, and a new theory would soon originate with an American. In 1909, Thomas Jefferson Jackson C. was a U.S. naval captain based at Mare Island near San Francisco. His official job was to keep the standard time for the U.S. West Coast. But C. was also a gifted scientist. As a young man, he had trained as an astronomer.
He was one of the first Americans to actually get a doctorate in astronomy. He went to Germany and got a PhD in astronomy, which was, almost unheard of back then. The U.S. was still scientifically total backwater in the 1800s.
C's duty station, Mare Island, had an observatory, and the captain's job allowed him plenty of time to theorize. He had spent time analyzing both the co-accretion and the fission hypotheses regarding the origin of the moon, and he wasn't convinced. Gradually, Thomas C. developed a completely different idea. It came to be called the capture theory. Essentially, C theorized that the moon had actually formed in a different part of the solar system from the Earth, that it orbited the sun, just like the other planets, but that at some point it had moved too close to Earth and was captured by Earth's gravity.
His idea was that there's something that he called the resisting medium in outer space, which we know is not there now.
C never adequately explained what this resisting medium was supposed to be, possibly tiny particles of matter. Regardless, he was sure it no longer existed.
His idea is that for the Earth to capture the moon would have to come in from far away, and then it would hit this resisting medium and slow down, and then gradually get captured into an orbit. Maybe not at once, might take a little while, but gradually it'd be captured into Earth's orbit. It's a little bit like a bungee jumper jumping off a bridge. They'd go down, come back up, not quite as far, go down, come back up. And eventually they'd settle down at the bottom.
Thomas C.'s capture theory would certainly explain the difference in iron content between the Earth and the moon. If the moon formed elsewhere, its composition could be very different. On the other hand, the notion that Earth's gravity could capture and retain such a large object was unlikely, since there is no obvious resisting medium to slow down an object as big as the moon. All three theories had significant weaknesses. The origin of the moon remained a mystery. On July 20th, 1969, U.S. astronauts set foot on the lunar surface for the first time.
It's one small step for man, one giant leap for mankind.
They had landed their lunar module on the hardened lava plain known as the Sea of Tranquility. And mission pilot Buzz Aldrin described the view as magnificent desolation.
Beautiful view. Isn't that something? Magnificent sight out here.
The astronauts brought back 48 pounds of moon rocks and dusty soil, or regolith. Geologists at Johnson Space Center in Houston eagerly awaited their arrival.
The excitement when samples first came back was just electric. I mean, it was just incredible. Nobody really knew quite what to expect. And we realized right away that we had basaltic rocks, like one might see in Hawaii. In fact, very similar to rocks one would see in Hawaii.
The NASA geologists were intrigued to find not only basalts, but rocks of another sort. Rocks called breccias. Breccias form during asteroid impacts.
So if you can imagine a large impact body hitting the moon is going to be very chaotic. It's going to throw up debris. Debris is going to come flying out of this, what winds up to be a crater after it's over, and you can see the many craters on the moon. This debris gets all jumbled up and lands on the ground around the crater, and then it gets compacted with the heat generated by the crater and gets turned into rocks that look very chaotic. You see all sorts of pieces in the rock of different sizes, different shapes, all pieces of the rock that were in the area that the impacting body impacted. We had just not seen anything like this on Earth.
The moon rocks soon began to tell a fascinating tale. First, the rocks and soil samples contained particles indicating that the moon must have been covered by a deep ocean of lava after it formed. This notion was reinforced by the discovery that the rocks were lacking significantly in what scientists call volatile elements.
Volatile elements are those that can evaporate easily and therefore be lost when you heat up a rock. And some examples of volatile elements include water or potassium, for example. And if you compare the bulk Earth rocks to lunar rocks, you find that the lunar rocks are extremely parched. It's as if they've been heated and they've lost a lot of their volatile elements.
But along with these stark contrasts, the lunar samples also revealed at least one astonishing similarity between the lunar surface and rocks and soil from Earth.
The isotopes of individual elements, like oxygen in particular, you have different forms of oxygen. The moon had exactly the same ratios of different forms as the Earth did. But all the other rocks we knew from elsewhere in the solar system, which are meteorites that fall out of space, all have different oxygen isotope ratios, which tells you that the moon material and the Earth material are very, very similar.
In the end, the lunar samples had supplied a wealth of hard evidence regarding the geological makeup of the moon. But astronomers trying to understand the moon's origin were still left with a puzzle. For William Hartman of the Planetary Science Institute in Tucson, Arizona, the information gleaned from the moon rocks supported some ideas he'd been working on for nearly a decade. Now a distinguished astronomer and painter of space images, in the early 60s, Hartman was a graduate student at the University of Arizona, taking part in a project to map impact craters on the moon. From the enormous basins, or seas, to the smallest visible dimples.
We realized during this mapping in the 60s that the big basins are actually impact features. Very large asteroids hit the moon and made these huge explosions. Some of those are 600 miles across. How big an object does it take to do that? Something like 100 miles across. So we had large objects running around in the inner solar system as the Earth was forming, and they were crashing into planets.
For Hartman, the notion that 100-mile-wide asteroids once impacted planets begged a couple of questions. Could planet-sized objects have ever collided? And could that have something to do with the formation of the moon? By 1972, Hartman and fellow Tucson astronomer Don Davis had created a computer program to help them explore these ideas. The program made a rough attempt to simulate the accretion process in the early solar system. The astronomers wanted to see if any other planetary bodies formed near the Earth that could have crashed into it.
The idea was if there was some other body there and it finally crashes into the Earth, blows off all this crustal material from the Earth, as well as from the impactor itself, maybe the moon could form out of that.
Sure enough, the simulation showed that a second planet could have formed in the Earth's accretion zone, one about the size of Mars. It wasn't the moon, because it had formed from the same elements as the Earth and should therefore have had the same iron core and heavy density as the Earth. The moon, of course, does not. That was evidence enough for Hartmann to formulate a new fourth hypothesis. It came to be called the giant impact theory. In 1974, a new hypothesis explaining the origin of Earth's moon debuted on the world's scientific stage. Its proponents dubbed it the giant impact theory.
The basic idea is that about 4.5 billion years ago, Earth collided with an object roughly the size of the current planet Mars. It's a very large collision, and it started the Earth spinning. It's what gave us our current 24-hour day, we believe. And this collision was so massive that it launched material into orbit around the Earth, and it's from that material that we believe the moon later coalesced.
Dr. Robin Canup and others at the Southwest Research Institute in Boulder have constructed a computer model to study the details of the giant impact scenario.
It divides up the Earth and this colliding rogue protoplanet into many different particles, and then the evolution of each particle is tracked through the course of the impact.
The simulation depicts the impact from a bird's eye view, from the top down.
The Earth was probably partly molten even before this impact. So initially, the impactor came in from this direction. It hit the Earth with an off-center collision. And you can see the impactor has been stretched out into this long arm of material right here.
Scientists believe the upper layers of the Earth became completely molten following the impact.
The collision starts the Earth rotating. And you can also see that the collision has substantially distorted the shape of the Earth itself. After a couple hours, we see that this arm of impactor material has coalesced gravitationally into two large clumps. The inner clump of the impactor material is actually composed overwhelmingly of the impactor's core, so that when this inner clump recollides with the Earth, which happens right there, the vast majority of the iron that came in with the impactor is actually accumulated by the Earth. While this outer clump comes in and makes a close pass by the Earth and is stripped by the Earth's gravity into a long arm of material, which then breaks up to form this disk.
The material is thought to have coalesced to form the moon in less than a year following the massive impact. There is no sign of this impact on the Earth today, because at the time, our planet had only developed to about 90% of its current size. The remaining 10% would accumulate from later, much smaller impacts. Also, the Earth's own gravity had a reshaping effect.
Within a day after the impact, the Earth had reassumed a basically spherical shape, and any depression that the impact caused would have been smoothed over.
Giant impact theory originator Bill Hartmann presented his hypothesis at a scientific conference in 1974. But it received little attention for nearly a decade. Interest in the moon dropped off sharply at the end of the Apollo missions.
Beautiful, very smooth, very quiet ride.
Finally, at a lunar conference in Hawaii in 1984, 12 years after the last moonshot, the world's foremost astronomers reached a consensus. The giant impact theory was the most acceptable explanation to date for the origin of the moon.
I think there's still some people who say, okay, it's not really proven yet, but It's what I would call the default theory. If you look at any textbook of planetary science or geology, it's just the theory that's accepted. And there are certain small discrepancies which have yet to be explained, but by and large, it works.
Even with an agreed-upon theory of how our moon came to be, scientists have not finished studying our closest cosmic neighbor by any means. In fact, talk of returning to the lunar surface with a permanent manned outpost has recently emanated from the White House and NASA headquarters.
Gorgeous views out the window. Sequence good, everything go.
Such a base could provide a place to train astronauts to live in space long-term, as well as provide a more efficient launch point for eventual missions to Mars. But such lofty scientific goals are far from the minds of average residents of Earth, who occasionally peer up at the glowing, mesmerizing lunar disk in the night sky. For us, talk of lava oceans, regolith-forming micrometeorites, and giant impacts will never diminish the fascination and romance of our mysterious neighbor world, the Moon.